The main topic today is the dot product. Right off the bat, I'll say that this is not its only name. Also known as inner product. Though at the same time, I will tell you that dot product is more commonly used when we're dealing with geometric vectors like we are. So we will tend to say dot product. The idea of an inner product is more general. It applies to a wider variety of situations. To add on even more confusion, I'm not going to write this down. In some physics textbooks, they'll even call it a scalar product. That's worthwhile to emphasize that the answer of a dot product is a scalar, a number, but that's just too many names. So we will just stick to calling it a dot product. I would like to reserve the letter U in this context for unit vectors, unlike the textbook. So I'm going to typically use V and W instead. Suppose we've got two vectors V and W. These could be two-dimensional vectors. I could write two components for each. But I will just write these equations as if they're three-dimensional vectors. Just realize the same kind of equations would hold for two-dimensional vectors. So the components of V are V1, V2, and V3. The components of W are W1, W2, and W3. If these were two-dimensional vectors, I would not have a third component. V dot W, by definition, V dot W is the sum of the products of the corresponding components, is how to say it in words. Sum of the products of the corresponding components. Corresponding components are the first components, second components, third components. Their products are V1, W1, leave a little space, V2, W2, leave a little space, V3, W3. We want the sum of those products. Sum of the products of the corresponding components. That's what V dot W is. If they were two-dimensional vectors, this last term would not be there. There's actually nothing from stopping us defining this for four-dimensional vectors or five-dimensional vectors or 100-dimensional vectors or 1,000,000-dimensional vectors. Google dimensional vectors. Nothing stopping us from doing that except feeling afraid. Okay. Mostly we're just used to 2 and 3 dimensions, so we mostly stick with that. That's the main applications anyway. So we're typically good with that. N-dimensional vectors, where n is an arbitrary positive integer, can be defined, and also you can define the dot product for them. The dot, and I'm going to be a stickler about this and tell the graders to be sticklers, must be there. This must be there. Don't just put the V and the W next to each other without a dot when you mean dot product. Now, there's some teachers who might not penalize you for forgetting the dot. So there's some sloppiness out there. But I want you to put the dot there. We need to have that conceptual clarity to realize this is different than V times W or V cross W. There's a cross product as well as a dot product. That's the main topic for Wednesday. Today's topic is the dot product. They're different things and they both have their own symbol. So that must be there. Notice this dot product of these two vectors is a number. That's a number, a scalar. This is a scalar. So while V and W are vectors, their dot product is a scalar. When you write even in vector form, that whole thing represents a number, a scalar. Each piece is a vector, but the whole thing together is one number. That's the definition. However, you may know that that's not always how dot products are computed. If you happen to know the length of V, its magnitude, the magnitude of W, and the angle between V and W, it's a theorem that you can also compute V dot W as the magnitude of V times the magnitude of W times the cosine of the angle between them. I would like to verify this theorem if we have time today. I'm hoping we have time. It's based on the law of cosines from trigonometry, plus some properties of dot products. For the moment, before we talk about those properties, how do you use this? What's it good for? One thing it's good for is finding angles between vectors, because you can effectively take the equality of these things and solve for theta. So, for example, if V is the three-dimensional vector 1, 2, 3, and W is -4, 3, -2. I mean, I could try to draw these things in three-dimensional space and guess the angle, but that doesn't sound so pleasant. Much better to use the dot product and the equality of the dot product with this thing to solve for the angle. Then we know it precisely and we can approximate it well. So what do we have to do? We've got the equality between the dot product and this thing. We need to figure out the dot product, I guess, and we need to figure out these magnitudes. Compute the dot product, V dot W. Take the sum of the products of the corresponding components, 1 times -4, plus 2 times 3, plus 3 times -2. Make sure you're looking and double checking it in your mind. That's -4 plus 6 minus 6 is -4. The dot product being negative does mean the angle between them will be bigger than 90 degrees. It'll be obtuse instead of acute. So that's V dot W. What about the magnitude of V and the magnitude of W? Magnitude of V is the square root of the sum of the squares of the components of V. Guess what? I mentioned this, I think, last Friday. That's the same as the square root of V dotted with itself. That formula right there is more important than you might imagine. Not only for doing this calculation, but also for some theory, including the theory for why this works. Take the square root of the vector dotted with itself. So I do 1 times 1, 1 squared, plus 2 times 2, plus 3 times 3. And it seems like 14 is our favorite number, or square root of 14 in this class, because I keep picking vectors to be 1, 2, 3. W, its magnitude is the square root of W dotted with itself. Look at the components of W, that'll be -4 squared plus 3 squared plus -2 squared. Of course, the negative signs don't affect what happens when you square. 16 plus 9 is 25, plus another 4 is 29. Square root of 29. So now use the theorem. The dot product equals this. Therefore, -4, 3 dots means therefore. -4 is square root of 14 times square root of 29 times the cosine of the angle. So the cosine of the angle is -4 divided by the product of those two things. The angle is the inverse cosine of -4 divided by square root of 14 times square root of 29. That's fine for an exact answer. If you like combining the square roots and putting the negative sign out in front like that, you can do that. It's a product of square roots that square root of a times square root of b is square root of a times b. So I could do 14 times 29 here and get square root of 406 on the bottom. 4 divided by square root of that is about that many radians. We're taking the inverse cosine of the negative of that. Before I hit enter, let's think about it. Inverse cosine, inverse cosine. Inverse cosine takes a number between -1 and 1, which this is. It's about -0.1985. And returns an angle, if you want to think of it as an angle, between 0 and pi. I don't know if you remember that. It's in the first or second quadrant. 0 and pi radians. If the input to the inverse cosine is positive, the output is in the first quadrant between 0 and pi over 2. Our input's negative, it's going to be between pi over 2 and pi. So we're going to get an answer between radians between 1.57 and 3.14. 1.77. 1.77 radians. Multiply it by 180 and divide by pi. It's about 101.45 degrees. It's a bit bigger than 90 degrees. Okay, that's hard to draw accurately in 3 dimensions, but that's part of the benefit of this equality in the dot product equation here, is that you can find these angles without drawing too accurately. Of course, it could help you draw more accurately to know what the angle is. Since we could apply these ideas in even higher dimensions that we can't visualize, 4, 5, 10, 100 Google dimensions, you actually can figure out angles between vectors in Google dimensional space. Effectively, if they can't be drawn, how could you possibly find them? Effectively, this equality defines what the angle is even at higher dimensions. If I solve this equality more generally for theta, I could say theta is the inverse cosine of v dot w over the magnitude of v times the magnitude of w. Effectively, so we're saying in 2 and 3 dimensions, this helps us figure out what the angle is. In higher dimensions, that can't be visualized. Instead of helping us find the angle, it really defines what the angle is, even though it can't be drawn. Though you would have to be sure that this quantity, this fraction, is always between -1 and 1 in order for such a definition to work. That turns out to be true. It really will always be between -1 and 1, even in higher dimensional space. Though that takes proof, and it's a tricky proof. Effectively, it's called the Cauchy-Schwarz inequality. Don't say Cauchy. That really hurts my ears. Cauchy-Schwarz inequality is what says this quantity that I've circled is always between -1 and 1, even in higher dimensional space where you can't visualize it. And therefore, you can take the inverse cosine to define the angle. Is it useful to define such angles? That's not so clear. But I will say that dot products and more generally inner products do have plenty of applications, as people who took DiffyQ with linear last fall know. Applications to Fourier series, for example, and partial differential equations, but we're not getting into that.